So, can you imagine dragons? Okay. Today we're going to begin a new chapter. This chapter is on nuclear science. We'll talk about da 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 da. We'll talk about radioactivity and its many applications. I think you'll find this chapter about radioactivity interesting because radioactivity is one of these phenomena that we've only known about for a little over 100 years, but turns out to be extremely important. Now, the basis of the phenomena is that nuclei, when we're talking about atoms, in the center of atoms, that some nuclei are unstable. In fact, actually quite a few of them are unstable, and that they undergo reactions, sometimes spontaneous reactions, that lead to an emission of energy, sometimes an emission of particles or rays, and we call this radioactivity. And there are a number of applications of radioactivity, all the way from energy sources to radioisotope dating. Now, here are some images that we associate with radioactivity. On the upper left, when we say nuclear or radioactive, one of the things that usually comes to our mind is an image of an atom bomb. Yes, that is true. They can produce a phenomenal amount of energy as an explosive device, but we also think of nuclear energy as being a source of the production of electricity, nuclear power plants, as shown in on the left. We may also think of nuclear medicine. And you see a photograph here of someone injecting a isotopically labeled sample of some sort into someone's bloodstream for some diagnostic test. This may be injected to produce a bone scan, which is shown in the center of the slide. Another aspect of nuclear medicine, which we will talk about, includes radiation therapy, as shown in the upper right. Radioactivity can also be used in agricultural applications to sterilize fruit, produce. It's used quite a bit in research, and the bottom center is a drawing of how that might be done, injecting a plant or an animal with a radioactively labeled molecule to see what happens in terms of metabolism carried out by the plant or animal. We also use radioisotopes to determine the age of samples, both geological formation, rocks, but also human artifacts. We'll have a special lesson on radioisotope dating. And if those of you who still carry a watch, now I notice that a lot of young people don't wear wrist watches much anymore, but if you carry a watch and if it has an illuminated dial, it's very likely that you are carrying with you a small amount of some radioactive material. Usually these dials contain radium. In the top center of the slide, you see a universal symbol for radioactivity, the yellow sign with sort of 3 wedges or pizza slices. It's also important for you to realize that the energy produced by the sun is really a result of nuclear reactions, and we'll talk about the type of nuclear reactions in this section. Also, the internal energy in planet Earth, that is, the thermal energy under the Earth's crust that results in things like volcanoes and earthquakes, is largely a result of nuclear reactions occurring within the Earth. Now, if this is such an important phenomena, why have we only known about it for the last 100 years or so? Well, it took research. And the upper left of this slide shows you what I say, the smudge that led to the discovery. And here's a story. Henri Becquerel, a noted scientist and part of a family of noted scientists, happened to place a sample that contained uranium, inside a drawer wrapped in a black cloth on top of a photographic plate. Now, we call them plates then because that's what they were instead of film, but on a photographic plate. And he came back the next day, and even though there was no lights on, it was in a closed drawer and it was wrapped in a cloth, he saw that the photographic plate had been developed, indicating that there was some source of photons or electrons or something that was developing the film so that he could see the image of the crystals on the film. That's shown in the upper left. Now, he initially called this phenomena uranic waves because he knew that the samples contained uranium. So he called them uranic waves. And his discovery was around 1896. Other researchers who followed and worked with Becquerel at times were the Curies, Marie Curie and Pierre Curie. And it turns out that Becquerel and the Curies won and shared the Nobel Prize for the discovery of natural radioactivity. Marie Curie went on to win a second Nobel Prize, and so she is a very famous scientist in that she was the first female to win a Nobel Prize, and she's one of only two scientists who have won 2 Nobel Prizes in 2 different areas, the other being Linus Pauling. Now, on the next slide, we sort of define some terms. You always have to define terms. When we talked about atoms, we talked about a nucleus, the nucleus made of protons and neutrons. And we mentioned at the time that there existed what are called isotopes. That is, a given type of atom, a given element, such as hydrogen or carbon or sodium or sulfur or phosphorus, could exist as a number of isotopes. To be a particular element, you have to have a certain number of protons. So carbon always has 6 protons, for example. But that you could have different isotopes in which there were a variable number of neutrons. So while the most common form of carbon has 6 protons and 6 neutrons, there can also exist forms of carbon, what we call isotopes, that have 6 protons and either 7 neutrons or 8 neutrons. So atoms with the same number of protons but different number of neutrons are called isotopes. Now, we also refer to nuclides as the nucleus of these specific isotopes. Now, the reason we focus on the nucleus is that because in this chapter, unlike most of the chapters, most of the topics we're going to talk about, here we're talking about what happens inside the nucleus. Now, it's different in that most other kinds of chemistry and biochemistry and biology that we talk about involve reactions with electrons, where electrons form bonds between 2 elements, covalent bonds or ionic bonds to form large molecules, as big as DNA molecules. But in this chapter, we're going to only focus on the nuclei of elements, and it's immaterial as to whether or not they are part of a large molecule or just an atom by themselves or an ion or cation or an anion. So we refer to nuclides in this chapter because we're focusing only on the nucleus. The center of this slide shows a standard representation of an isotope in which we show C for carbon, the symbol for carbon, and we show that yes, it has 6 protons. For it to be carbon, it has to have 6, remember. But in this case, it's carbon-14, meaning that it has 8 neutrons because the mass number, the number on top, is the sum of the number of neutrons and protons. Okay, so if we see a 14, we quickly subtract 6 and we know there must be 8 neutrons in this particular isotope, or if we're focusing on the nucleus, this particular nuclide. So that's the definition of nuclides in the relationship with isotopes. Nuclear reactions, really we'll sort of break these down into 2 kind of categories. One is what we call a radioactive decay, which is a spontaneous reaction of a nuclide. A spontaneous reaction in which it emits something called an alpha or beta or gamma particle or ray. And we'll talk about these in the next slide. An alpha, beta, or gamma. A spontaneous emission of one of these particles or rays. Another category, and there's sort of a gray area in between these, but another category would be what we call transmutations. In a transmutation, a given nuclide reacts with either another nuclide or a small subatomic particle, such as a proton or a neutron or what we will call an alpha particle, that the 2 react together, and in doing so, sometimes they form bigger nuclides, sometimes they break up and form smaller nuclides. So a transmutation. In both types of reactions, the product of a nuclear reaction always is a different element than the starting material. This is like alchemy. Alchemists tried to convert lead to gold, but they were never able to. That's because they just didn't understand nuclear chemistry back at the time. Okay, so the bottom right shows an example of a nuclear reaction. This would be a radioactive decay in which uranium-238. Now, notice that uranium is an element that has 92 protons. So if I simply say uranium-238, I don't have to say the 92 because you could look it up in that periodic table. But uranium-238, that means that isotope of uranium, such that the sum of the protons and neutrons is 238, can react spontaneously to form thorium-234. TH is for thorium. And in doing so, it emits or ejects from its nucleus something called an alpha particle. Now here we've written it out as He, helium, because an alpha particle, as we'll see in the next slide, is really a helium nucleus. Types of nuclear decays. And we said 3 particles arrays. We said an alpha particle, a beta particle, and sometimes we call it a beta particle, sometimes a beta ray, and then a gamma ray, alpha, beta, gamma. An alpha particle is the largest particle that will be emitted in a spontaneous nuclear reaction. It actually is a particle containing 2 protons and 2 neutrons. As we saw before, it's essentially a helium nucleus. It is the biggest, the heaviest one that is emitted in these types of reactions. A beta particle or ray is actually a high energy electron that is emitted from a nucleus. It sort of shoots out or is kicked out of a nucleus of an atom, and we call this a beta ray. A gamma ray is a high energy photon. So whereas a beta is an electron, that is, it'll have a little bit of mass and a charge of -1. A gamma ray is a photon. It will carry energy with it, but no mass. Now, there are other particles or rays that can be emitted in nuclear reactions. We won't give many examples of these, but there's something called a positron emission. Positron just being the opposite charge of an electron. Yes, there are positively charged electrons, positrons. Something called K-capture or electron capture, and also sometimes nuclear reactions will involve the emission of small neutral particles as well, called neutrinos. When you have an INO at the end, this is, sort of comes from the Italian. It means little one, so neutrino. So you might want to think of your own name and putting INO at the end, and you can go ahead and say it out loud. You did, didn't you? Okay, caught you. This slide shows some nuclides. Some are stable and some are not. And these are some of the very common ones. Hydrogen, if we go to the left, the most common form of hydrogen has 1 proton, 0 neutrons. We talked about that in the chapter on atoms, on elements. There also is an isotope called deuterium, which has 1 proton, 1 neutron. So its mass number would be 1 plus 1 or 2. And there's one called tritium, or H3, and it is unstable. Tritium is unstable. It will undergo a spontaneous nuclear reaction. Now, this reaction takes a long time. It has what we call a half-life of 12.3 years. So it's not reacting very rapidly. And we'll talk about what we mean by half-lives in the next lesson. Another example would be carbon, which we've been talking about a little bit. We have carbon-12, the most common form of carbon, stable. We also have an isotope called carbon-13. Quick, how many protons and neutrons in carbon-13? 6 protons, that's why it's carbon. 13 minus 6, it must be 7 neutrons in carbon-13. And it is stable. But then we have carbon-14, which is an unstable isotope of carbon. It will undergo spontaneously a nuclear reaction. Now, this nuclear reaction doesn't occur very rapidly. Its half-life is 5,730 years. A very, very, very long time. The next slide illustrates these 2 types of nuclear reactions in a graphical way. The top box shows alpha decay, and it shows a certain nuclide, this one being plutonium, Pu, and it undergoes an alpha decay in which it emits an alpha particle, which is a 4-2, a helium nucleus, 2 protons and 2 neutrons, whichever the ones that are red and which are blue, leaving behind a smaller nuclide, this one being uranium-236. So this is an example of alpha decay. It always results in a new element with lower mass. The second example is beta emission. In beta emission, the example shown here, we start with a particular nuclide, this being radium-228. So if we have radium, radium can spontaneously emit a beta ray. Now in this drawing, I almost didn't want to pick this drawing because that little green thing is drawn much, much bigger than it is because it's an electron. It's a high energy electron that is essentially kicked out of the nucleus, comes speeding out of the nucleus, leaving behind actinide, another element, actinide-228. Now, if you remember from our chapter on atoms, because I know you're keeping up with all of this, that an electron weighs 1/2000th of the mass of a proton. Remember our red M&M and the little dot and all that? This is drawn much out of scale. This should have been, well, you should not have even been able to see it be so small if they actually tried to draw the electron. And besides that, it's moving very fast. It's being kicked out of the nucleus. So that would be beta emission. The result of beta emission will also be the new element. It will have the same mass. Notice that the masses are the same, 228 in each case, but a different atomic number. Instead of being 88 radium, it is now 89 actinide. Okay, so in each case, when we have a nuclear decay reaction, we form a different element. Okay, we'll pause now. As usual, ask you to do a little quiz before we come back to our next lesson. In the next lesson, we're going to focus on why some nuclides, some particular isotopes, why some nuclides are unstable, and we'll talk about this concept of half-life. And as we go out, we'll listen a little bit more to